review some of the reactions from this chapter. In the first reaction, a ketone is treated with acetic acid and one equivalent of iodine. In the second reaction, an alpha bromo ketone is treated with pyridine, which is a base, and heated. In the third reaction, symmetrical ketone reacts with excess chlorine and excess sodium hydroxide. In the fourth reaction, a ketone reacts with excess bromine, excess sodium hydroxide, and aqueous acid in the second step. Notice this is a methyl ketone. And the fifth and last reaction on the slide, unsymmetrical ketone reacts with LDA and an alkylating agent. In this first question, we have an unsymmetrical ketone and we're reacting with iodine, one equivalent, and acetic acid. So this will be an acid catalyzed alpha halogenation. This reaction generally will add an iodide or some other halogen to the more substituted side of the ketone. As long as that more substituted side has an alpha hydrogen, we can do this. So in this example, the left side here, the iodine should end up there by forming an enol that forms between the two carbons here, the carbon on the more substituted alpha carbon and the carbonyl carbon. And so for that reason, we have this as a product. When we add pyridine, which is a base, and heat an alpha halogenated ketone, we would do an elimination reaction. So we should get a double bond by removing the halogen and a hydrogen on the beta carbon. So in this example, we could remove a hydrogen from this carbon or this carbon. Either way, we're going to get the same product since it's going to be a symmetrical product. We have an excess of chlorine and excess of base. So this would be a base promoted alpha halogenation. So every alpha hydrogen of this ketone will be substituted with a chlorine. So for that reason, we get this as a product. In the next reaction, this is pretty much the same reaction as reaction C, except that we're using a methyl ketone, so there's a twist at the end. So after replacing all of the alpha hydrogens on this methyl group with bromine, the sodium hydroxide will do a substitution reaction through this carbonyl and eliminate the carbon with the three bromines on it, so you end up with a carboxylic acid. Note that the second step is acidic or aqueous acid, so for that reason we get the aqueous acid as opposed to the conjugate base of the aqueous acid. Adding LDA to an unsymmetrical ketone will lead to deprotonation of the least substituted alpha hydrogen, so that would be the hydrogen on this carbon, and then that forms an enolate there, which can attack this alkylating agent, so attack the carbon with the leaving group, the tosylate, and you add a benzyl group, which is a CH2 to a benzene ring. Here's a few more reactions for this chapter. So we start off with a beta ketoester, and we're going to add LDA and methyl bromide. In the next reaction, we're going to use an unsymmetrical ketone, add LDA at low temperatures, and then TMS chloride. In this third reaction, we're going to use a siloprotected enol, react it with TBAF, followed by aqueous acid. And then lastly, we're going to have this beta ketoester, and we're going to add sulfuric acid, water, and heat it up. When you have a 1,3-dicarbonyl such as this, and you add base like LDA, you will remove the hydrogen that is in between the two carbonyls, That's the most acidic hydrogen. You form an enolate there. That enolate will react with an alkyl halide to add an alkyl group at that position. So methyl bromide will lead to adding a methyl group there. In the next example, we have an unsymmetrical ketone. By adding LDA at low temperatures, we will form the kinetic enolate. So one way of looking at this is LDA will remove this hydrogen. That enolate that forms has two resonance forms. So we can move that negative charge towards the oxygen and form this enolate that is sort of shown here trapped with the silicon protecting group. So that oxygen will react with TMS and attach the TMS group. Remember, TMS is short for trimethyl silyl. So it's a silicon attached to the oxygen with 3 methyl groups. In the next step, TBAF, which is a fluoride source, will remove the silicon protecting group, exposing the enolate, and then that enolate will be protonated to become a ketone. There's two ways to look at it. When you protonate this enolate, you get an enol, and enols are always in equilibrium with the carbonyl. Another way of looking at it is this. Once you expose the enolate, we can form the other resonance form, which would be moving the negative charge to this carbon and moving the double bond between the carbon and oxygen. And then that negative charge on this carbon will be protonated by aqueous acid, giving you the ketone. In the last step, when we add sulfuric acid and water, the first thing that's going to happen is this ester will become a carboxylic acid. And by having that carboxylic acid with a beta carbonyl next to it, it's going to decarboxylate. So in other words, you're going to remove this group here entirely, and you end up with a ketone. In this synthesis problem, we'll need to convert a 1,3-diester, which by the way is diethyl methylate, into an amide that has a cyclohexyl group at the alpha position. Looking at the reactant versus products, one of the things we have to recognize is that esters are interchangeable with other acid derivatives. As we learned in the ethyl substitution, you can take different acid derivatives and convert them into each other. So we can presumably convert one of these esters into an amide. As far as adding the cyclohexyl group, one of the ways we can do that we learn in this chapter is by doing an alkylation of the alpha position. So that would be this one here, with a dihalide, an alkyl dihalide, that would allow us to essentially do two substitution reactions with the halogens to add the two sides of the dihalide alkyl group. The other ester can be removed, as we learn in this chapter, by first hydrolyzing the ester into a carboxylic acid and then doing a decarboxylation. So the way we would answer this problem could be that we add base to deprotonate this position, and then add a dihalide so that we could add the cyclohexyl group. So notice that cyclohexyl group has 1, 2, 3, 4, 5 carbons. The 6th carbon is actually the alpha carbon. So we need to have a dihalide that has 1, 2, 3, 4, 5 carbons, 2 halogens on each end. And then if we add an excess of this base, we should be able to cyclize that chain by forming the enolate first, which would attack one of these carbons, do a substitution, eliminate this leaving group, and then if we add enough base, the reaction can repeat. So the second alpha hydrogen can be removed, which would then attack the other end. So this carbon chain is already attached by the first reaction, so we can now attach this side and cyclize that ring. Now we have this as a product, and if we add sulfuric acid, water, and heat, we can hydrolyze the two esters into carboxylic acids. Since the carboxylic acids are 1,3 to each other, In this reaction, when we're heating, we're going to decarboxylate one of them. And so for that reason, you see the product here with only a single carboxylic acid. The other carboxylic acid, which used to be on the right side here, will be eliminated as a CO2 molecule. Last step is taking this carboxylic acid and doing an acyl substitution with the appropriate amine. So if we want to add a nitrogen with an ethyl group, we have to add this primary amine with an ethyl group. Adding DCC will make the reaction easier, so we can do the reaction at room temperature. And so that will convert the carboxylic acid into the amide, that you see in the product.